In this video, we are going to talk about valence shell electron pair repulsion, or VSePR for short, where the E is little because it looks like the little e with the negative sign on it for electrons. So what is valence shell electron pair repulsion? Well, electron pairs repel. It's basically that simple. And when they do, the atoms in a molecule are forced to spread out to minimize this repulsion. Meaning, these two atoms that might be attached to the central atom that you see here, how are they going to orient themselves? Are they going to be really close to each other? Are they going to be spread out? How are they related to each other? Well, they're going to spread out because they both have these nice electron clouds in these valence shells, okay? And they repel each other. So all these electrons are going to repel each other. So they're going to spread out as best they can to repel each other. And so, for instance, with this molecule, which is called linear because it's in a line, it spreads out 180 degrees, because if it spreads out 181 degrees, now it's closer in this direction than it would like. So it just spreads out to minimize that repulsion. But it's all still in a plane. Same thing with this one, still in a plane because it realized 120 degree separation, every circle is 360. So that was the best way to minimize that repulsion. We get more complicated as we add more things around that central atom. Things could be either atoms, or it could even be electron pairs that are free electron pairs on that central atom. But the idea is these are still electron dense regions that are going to repel each other, and therefore they're going to create these pretty shapes in order to have in order to have the lowest energy configuration possible, because once again, atoms want to be in the lowest energy state. And so you'll see these different configurations, and we'll talk about each one and what they're called. So the idea of this lecture is that if you know what a molecule's Lewis structure looks like, you can predict the 3D shape that it might take in the real world. So I have this chart that I've made that helps us classify different types of molecular and electronic geometries based on what the atoms are that make it up. Now, how do you read this chart? Well, first off, it says total number of electron pairs around the central atom. I'm going to call these in this lecture things, because it could be atoms, like you see here drawn, okay? Or it could be electron pairs, but I'm going to consider electron pairs or atoms as things. And so, for instance, there are two total things around this central atom here. So if this is my central atom, there are two things around it. And if that's the case, it's going to be considered linear and linear. But you might be thinking, what's the difference between molecular geometry and electronic geometry? Because geometry, you get it, how things are arranged in space. But what's molecular? Well, I want you to think of molecular geometry as, what do the shape of all the atoms around the central atom look like? So this, everything is in a line. So if you connect all the atoms, it looks like a line. But then what about electronic geometry? This is the shape of everything, including any electron pairs that are around the central atom. And so it includes those electron pairs, whereas the molecular geometry is just the atoms that are attached, not extra things like this here, this electron pair. So, for instance, if you have two things around the central atom, as you see in this picture, you have the exact same molecular geometry as you have electronic geometry, because it's just going to form a line. Okay, you're not typically going to have a lone pair on here. Okay, and so that's what these columns are for, the number of bonding pairs versus non-bonding pairs. Bonding pairs would be how many things are involved in a bond, whereas a non-bonding pair would be like this. You have a free pair coming off of the central atom. So that's what these two columns mean. Okay, I'm not going to focus too much on these two columns because I'm just going to call them things, and I think that's going to simplify things. All right, so in this next example, though, we have three in both of these examples, and so there are three things around the central atom. And so the electronic geometry is not going to change, but the molecular geometry will. And so when you have three things around the central atom, if we look at the shape of everything, including electrons, it looks like a triangle that is all in the same plane. Okay, so we're looking at just that. And so the shape of the atoms is the same because there's no lone pair. So it's the shape of all three things forms a triangle, trigonal, that's all in a plane like a sheet of paper, and so it's trigonal planar. This is the first one whose molecular geometry is different than our electronic geometry. So for the electronic geometry, we're looking at the shape of everything, including electrons. So that forms a triangle. And so everything that has three things around the central atom is going to have that same electronic geometry. But the molecular geometry is going to change depending on if those things are atoms or if those things are electron pairs. So in this case, we're going to look at the bent molecular geometry. We're only looking at the shape of the atoms. So these atoms, it looks like a line that's been bent because we're only connecting the atoms in space. We're only looking at this structure, and so this is bent. Let's look at these examples a little bit more, focusing first on those that have two atoms attached to the central atom. Let's look at carbon dioxide as an example. So CO2, carbon dioxide. Carbon has 4 electrons in its outer shell. Oxygen has 6. There are 2 of them. So 6 times 2 is 12, plus 4 gives us 16 electrons. So when we draw carbon dioxide, you start out first with your skeleton with the least electronegative in the middle, and then you place electrons all around it. Now we know carbon is going to want to have 4 bonds around it. And so if we give those each 2, and we know this is 16, which is divisible by 8, that's going to give us 8 around this oxygen and 8 around this oxygen. So we would draw it looking like this. And we can see pretty quickly how we might consider this linear. Here you have an oxygen and another oxygen, and then your central carbon is here located in the middle of the structure. So this carbon has 2 things attached to it, 1, 2, which means its electronic geometry is linear and its molecular geometry is also linear. And so it's spaced out in space just like you see in this picture here, where the 2 oxygens are as far apart as they can be from each other, which is good because oxygen is really electronegative. It's got a high electron density around it, and so it wants to be separated in space. Next, we're going to look at those VSePR diagrams for things that have 3 things attached to a central atom. Now, in this case, it's going to matter that it's not just atoms, because when you have 3 things, one of them can be a lone pair. So let's look at that first example, that of trigonal planar. Something that could be it is BH3. So remember, your boron has a total of 3 electrons in its outer shell. Hydrogen has 1, but there are 3 of them. So that's going to give us a total of 6 electrons. And so that's why even though boron doesn't have a filled valence, it's happy, it's satisfied. So you're going to have boron in the middle with 3 hydrogens outside. How is it going to orient? These hydrogens are going to try and separate each other in space. And so you end up with this trigonal planar molecular geometry and trigonal planar electronic geometry. It's the same. But now let's look at something such as SO2. So with sulfur, you have 6 electrons. Oxygen, you have 6 times 2. So we're going to have a total of 18 electrons on our species. So we put our least electronegative in the middle, which is sulfur. And then we also have oxygens coming off of it. And then we have a lone pair here in the middle. Now, in order for our octet to be satisfied, we need some double bonds and we need some electrons. We check and see, have I drawn 18 electrons on my Lewis structure? 8 electrons here, 8 electrons here, that's 16, 17, 18. Yes, I have. And so in this case, it definitely has this bent structure that you see here, where this lone pair correlates with this lone pair. This atom is 1 oxygen, and this atom is the other oxygen. And sulfur is my atom in this middle, my central atom. And so in this case, my electronic geometry is still trigonal planar because that's pretending like I'm including my electrons in this diagram. But my molecular geometry is more of a bent shape. And so this is where it helps to kind of think about, all right, if I ignore the electrons, what shape is it? Is it a line? It may look like a line if you draw it like this, but it's not because it's bent because of these 2 electrons up top. All right, so this is where it kind of helps to try and draw the configuration in space like you would. Sometimes I'll be like, all right, let me just draw my stick figure and see what it looks like. Oh, hey, that's what it looks like. It's trigonal planar. And then this is my electron pair, and so it's bent. Okay, but that's just kind of what you want to do, is you want to go from Lewis structure to electronic geometry, and then see if you have any free pairs, and if you do, it's not going to be the same as the electronic, and so it's going to be something else. And then think about what shape is formed. Next, let's look at VSePR for when we have 4 things attached to the central atom. So in each of these cases, it's called tetrahedral. Tetra meaning four with a hedral structure. So we've got a tetrahedral structure. Now notice you could have either one free electron pair or two electron pairs. And in each case, the molecular geometry is going to change. Let's look at each one closer. So this one here is tetrahedral. So we have carbon tetrachloride. One carbon, that's your central atom, with four different atoms attached around the carbon. And so in this case, you have a tetrahedral structure because you have a central atom and four things, which all happen to be atoms, attached to the outside of it. Next, we have something that is trigonal pyramidal, that of NH3. So if you have nitrogen, that's 5 valence electrons. Hydrogen, that's going to be 3. So we need a total of 8 valence electrons drawn on my structure, or 1 times 3 to give me 8. So when I do that, I have nitrogen, bound to a hydrogen, bound to a hydrogen, bound to another hydrogen. But that is only 6 electrons, so I need 2 more electrons, and I can draw those on my central atom. So now you can see the correlation as to how that free electron pair is shown here, and then I have each of my 3 species, my 3 atoms coming off of my central atom. And so that's why it's called trigonal pyramidal, because now this kind of looks like a pyramid, but one whose base is a triangle. Okay, so that's why it's called trigonal pyramidal, or trigonal, however you want to say it, pyramidal. You've got a triangle base. All 3 of those corners come up to a point here in the middle. But the electronic geometry is still tetrahedral because you still have 4 things connected to the central atom. So 4 tetrahedral. Let's do another example of tetrahedral. You still have 4 things attached to it, but now it's going to look bent, just like we looked at previously. It's going to be bent because the molecules are oriented in space to arrange themselves away from these 2 electron groups. Water is our classic example of this. So oxygen has 6 electrons, hydrogen has 2, or 1 times 2 is going to give me 8 valence electrons around the central atom. So if I connect oxygen and I just do it like this, and connect my 2 hydrogens, and then I put my 2 pairs that remain to give me my 8 electrons used up, water looks like this. And so a lot of students will go, oh yay, that looks linear to me. And this is where you're going to put a giant X through it and say, no it doesn't, it's going to be bent. Because your electron structure is going to, these electrons here are going to orient in space to force the 2 hydrogens away from it. Okay, now I know it's a little hard to look at in this diagram, but you do actually have your one group here and then your other electron group here. All right, so if I ask you, what is the electronic geometry for water or dihydrogen monoxide? You'd say tetrahedral because there's 4 things attached to the central atom. But it's going to be bent because the structure for H2O, the molecules themselves, or the atoms, excuse me, are not in a line. They are bent. The hydrogens are pushed away from these very, very negative groups of my electron pairs.